Welcome back, Chemistry 30. So we did this example together, and I left you with this one to try. So what I'm going to do is just rewrite this a little bigger, just so that it's easy to write in all the oxidation numbers, write what's reduced, write what's oxidized, etc. So here we have chlorine. It's a halogen. The group 7s tend to have a charge of -1, right? Because they all want to gain 1 electron, which means their oxidation number is going to be -1. -1 times 4 is -4. I know that's going to be 0 because there's no charge here. So that means all the tin contributes plus 4. And since there's only 1 tin, it must be 4. Iron by itself is 0. And this tin, we can see it must be plus 2. And this iron must be plus 3, such that that works out like that. So we can see here the tin, it's getting lower in oxidation number. It's getting more negative. To get more negative or to decrease the oxidation number, you must be being reduced. Gain electrons, reduced. And so the net change to go from plus 4 to plus 2, there's a net change of -2, right? Iron is the next one. Cl remains unchanged. -1, -1. So we're okay there. Iron is going from 0 to plus 3. It's more positive, which means it's losing electrons. Lose electrons, oxidation. And its net change is going from 0 to plus 3, plus 3. All right? So here I have a -2 and I have a positive 3. The lowest common multiple for 2 and 3, of course, is 6. So if I have 3 of these -2s, I'll have -6. If I have 2 of these positive 3s, I'll have positive 6. So you can see what I need to do here. The coefficients, I need to have 3 tins to make the correct reduction number, and I need 2 irons to make the correct oxidation number there. So we'll do that. So for every 1 tin, there's a change of -2. So if I have 3 of them, that'll mean we'll have a change of -6. So we'll put 3 here. And for over here, of course, we need to double the irons. There we go. So let's see what we got here, because now, so we've done basically those first few steps. We did that, we did that. We made the oxidation numbers equal by adjusting the coefficients. So let's see if we need to use conventional means now. So 3 tens and 3 tens, we're good there. 3 times 4 is 12 chlorines. 3 times 2 is 6 chlorines. 2 times 3 is 6 chlorines. So 6 plus 6, I have 12 chlorines there. And then 2 iron, 2 iron. So guess what? We're good there. It's balanced. Okay? So on the assignment, I think the first few questions involve balancing like this. So yeah, so questions number 1, A, B, and C from the EC1.2 assignment are like this. All right, now the second part of this looks at balancing net ionic redox equations. So sometimes chemists prefer to express redox reactions in the simplest possible terms, i.e. an equation showing only those substances that are oxidized and reduced and nothing else. So if we look at an example like this, this is one that we did for the first example we did. Copper plus nitric acid giving copper 2 nitrate, etc. Note that the reaction takes place in aqueous solutions. So HNO3, which is a strong acid, will be ionized. Likewise, copper 2 nitrate will be dissociated into ions as well. Therefore, we could write the equation in what is referred to as ionic form, showing everything that's aqueous in terms of ions. So solid copper just stays a solid copper. Nitric acid, though, since it's a strong acid, it exists as hydrogen ions and nitrate ions floating around. And since we have 4 nitric acid molecules here, we'll have 4 H's floating around and 4 nitrates. So this 4 applies to the H's, right? Because if I had 1 of these, it'd be H plus NO3 minus. But since I have 4 of them, there's 4 of each. Copper nitrate, for every 1 copper I have floating around, I have 2 nitrates floating around. This is a gas form, so it just stays together, and this is liquid, so it just stays as liquid. Okay, so that's considered to be ionic form. Anything that's aqueous is dissociated into ions. You can see that there are 4 nitrate ions among the reactants, but only 2 of them undergo change to form nitrogen dioxide molecules. What's the role of the other ones? The other 2 are called spectator ions. So they're just kind of spectating, not participating in the reaction. They're just sitting there. And we can eliminate those. So 2 of these become unchanged as 2 nitrates over here. So we can get rid of 2 and 2 from here because they're not participating in the reaction involving oxidation, reduction. So to simplify things, when running redox equations in ionic form, chemists usually indicate hydrogen ions by H+ with the understanding that, yes, they're H3O+. The equation can then be written showing the substances that are undergoing a change. So 2 nitrates remain unchanged. So I take 2 away from here, leaving me with 2. Take all of these 2 away, leaving me with none. So now I just have this. And if I look at the equation in unbalanced form, so get rid of the coefficients, we have this. And if I'm looking at the substances that are only oxidized and reduced, so here we know that copper is undergoing oxidation. And let's see here, -2, 2 times 3 is -6, but there must be a charge of -1 overall, right? So that means this is +5 + 5 to equal -1. And then over here, -2, -4. There's no charge here, so must that have to be 0. Look at that. So this nitrogen is getting reduced. So you can see the things that aren't doing anything in terms of redox are the H and the H2O, so they get omitted. And then I just have this. So in this case, the hydrogen ion and water molecules are eliminated because neither is oxidized nor reduced. The only additional information needed is that the reaction takes place in an acid solution. So we're kind of showing you what the net ionic equation looks like, and this is what it would look like in terms of a redox equation. And so if we had started with this and balancing this, we would have to have known if it's an acid solution or basic, so I'd have to give you that. Because, hey, we're kind of working backwards here, breaking it apart, and we knew it was in an acid solution because of the HNO3. In the acid solution, hydrogen ions and water are abundant and can participate as either reactant or product. So if we look at the next page, some redox reactions could occur in basic solutions. When we have that, we can add hydroxide ions and water molecules because they are abundant as well. Basic solutions have abundance of OH instead of the H pluses. So if you try to balance the equation above, you'll see that it appears upon. So that equation that we ended up with here. So this whole page is just simply breaking something down into the net ionic equation for a redox reaction. So if I just draw that here, so if you had been given this to start off with, so a net ionic equation, and if you tried to balance it, so what we did earlier here, we wrote down the oxidation reduction numbers, right? Charge of -1, charge of -1. Okay, so if we had done this, so we know that, of course, copper went from here to here, which is 0 to 2, so that's oxidized, right? Lose electrons, oxidation. And at a change of +2, nitrogen went from +5 to +4, so we know that's reduced. And going from +5 to +4, that's a change of -1. So, of course, 2 and 1, the lowest common multiple is 2. So if I have 2 of these, I'll get what I need. So put a coefficient of 2 in front of the nitrates. So put a 2 there. So my nitrogens are good, my coppers are good, but darn it, look at what happens here. 2 times 3 is 6 oxygens, 2 times 2 is 4 oxygens. So it seems impossible here. But since we were told that it was in an acid solution, we can manipulate things. If, of course, we had started off with this, on the previous page we kind of worked backwards, but the actual question would be, you're given this net ionic equation, balance it if it's in an acid solution. So over here, kind of 2 steps. Add H2O to the side that is short of oxygens. Okay, so we're going to add water over to this side because this is where we're short, right? 6, 4. So I'm short 2 oxygen atoms. So I'm going to add water to this side in the effect of 2 to give me my 2 oxygens that I need. And then add H pluses where you are short H plus after water has been added. So of course over here I'm going to be short because I don't have any H's at all. So I'm okay with oxygen. I added water to this side to make up for the oxygen I'm short of. And when I did that though, I added, let's see, 2 times 2, 4 hydrogens. So I need to add 4 hydrogens to this side. And if you notice, going back to here, that is in fact what we had originally. 4 H's, 2 H2O's. 4 H's, 2 H2O's. So what we did is we worked backwards to figure out what I must have originally had there. And I think if we look here, we're all good. 1 copper, 4 H's, 4 H's, 2 N's, 2 N's, 6 O's, 4 plus 2 is 6 O's. Okay? So maybe try to do this one here the same way. It is in an acid solution. So you'll get to a point where you're short of oxygens, add waters to that side, and then hydrogens to the opposite side.